Okay, section 1.1 is all about angles. This is, again, going to be a review from geometry. In fact, most of the things that are in this section are just vocabulary to make sure we're all on the same page with what I'm talking about when it comes to angles. Very little should be a surprise for you. And in fact, I'm not even going to read all of the bits and pieces written on here because they're just definitions that you probably already know. So we're going to fly through the first few pages, just highlighting words I want to make sure you know. And if you don't know them, actually go read the blurbs. So when it comes to geometry and the beginnings of angles, we have to know points, lines, and planes from geometry. So if you have a line, the line AB has no endpoints, but it has the points A and B on it. A segment does have endpoints. And a ray only has one endpoint and has a line that extends forever on the other side. So when we're making angles, we're making them out of points, lines, and planes, but it's specifically two rays, a terminal ray and an initial ray. So for these angles, when we're talking about angles, again, these are two rays. You'll have your initial side of the angle and then your terminal side of the angle. So these two words I'm going to use a lot, initial side and terminal side. That's showing you where you start and where you end for the angle, especially on a coordinate grid. Your initial side is usually going to be the x-axis, but I digress. When we are working with angles, there's two directions we can take angles. A counterclockwise rotation, which is this direction. That's an ugly arrow. Let me try that again. This direction. That is a positive angle. When we go clockwise, that's going to be a negative angle. So you have an image of this right here. This one is a positive angle because we are going counterclockwise. This is a negative angle because we're going clockwise. And we will be going both positive and negative angles. As we rotate around, a rotation can consist of more than one complete revolution, which is all the way around. Again, we'll just put this here. This is a positive. This is a negative. Just getting us on the same footing with vocabulary. Hopefully none of this is super new because it's just some geometry concepts. Flipping it over onto the back, we have our degree measures. Now, those of you who've taken pre-cal know that eventually we will start measuring in what's called radians, but for the first few chapters of this book, we're working only in degrees. So let's make sure we know what a degree is. We've been using degrees for a long time. The Babylonians, 4,000 years ago, started to simplify this into a measurement. They assigned 360 degrees to a complete revolution of a ray. So they looked at a circle, essentially, and they said, all right, that's going to be 360 degrees, which means that 1 degree is 360th of a rotation. So they've determined what this degree measurement is comparing to a circle. We've used degrees before, nothing new. But there are 4 types of angles that we studied in geometry. You have your acute angle, which is between 0 and 90. You have your right angle, which is exactly 90. Obtuse angles between 90 and 180. And the one everybody forgets about, your straight angle, which is exactly 180 degrees. It looks like a straight line, but technically it could also be a straight angle where the rays are opposite rays. 2 more vocabulary words from geometry that we need to know are complements and supplements. If we're talking about complementary angles, we're talking about angles that add up to 90 degrees. They are complements of each other when they do this. When we're talking about supplementary angles, they add up to 180 degrees. Does this sound familiar from geometry? Yeah, might have forgotten the exact words to use, but complementary and supplementary are the type of angles. So let's just do a quick example here. Find the measure of the complement and the supplement of an angle measuring 40 degrees. I'll do the complement in blue and the supplement in green. So if we know that the angle we have is 40 degrees, bless you, to find the complement, we know that we're looking for some angle to add with 40 degrees to equal 90 degrees. I could have made that an algebra problem, but instead I'm just going to put a little box there. Bless you again. What angle would I have to put in that box? 50. So the complement of 40 degrees is 50 degrees. Now I want to make sure that you're being specific enough with yourself here. You have to put the degree symbol for it to count, or the word degree after it for it to count. Otherwise, and eventually, you're counting in radians, which is completely different. Okay, if we're finding the supplement from 40 degrees, that means we would do 40 degrees plus something would be equal to 180 degrees. We can do this in our sleep. What is the supplement? 140 degrees. Very good. Okay, so complements and supplements, very easy. Almost too easy, so let's make it a little bit more challenging. In the example number 2, it wants us to find the measure of each marked angle. They're inherently giving us information about whether it's complementary or supplementary. In this first image, are these two angles complementary or supplementary? Complementary because they add up to 90, so we're going to put a complementary. I always spell this word wrong, so please ignore. It's just one of those words. You know those words you just never spell right? Necessary, complementary, restaurant. I always misspell those words. I don't know what it is. But since we know it's complementary, that means we know that the two angles, 6x degrees and 3x degrees, should add up to how many degrees? 90 degrees. Now when we're solving this, we can lose the degrees symbol for a second as long as by the end you put it back. So if we combine like terms, that's going to be 9x equal to 90, or that x is equal to 10, which is not what it's asking for. It's asking for the measures of the angles. So if x is equal to 10, then 6x is going to be equal to what? 60 degrees. And 3x is going to be equal to what? 30 degrees. So those are my two angle measurements, 60 and 30. As a quick check in my brain, is 60 plus 30 90? Yes. Okay, we're done. For the second one, how are these two angles related? They equal 180, so they are supplementary. They equal 180. So we'll do the exact same thing. We can do 4x degrees plus 6x degrees. This time it would be equal to 180 degrees. We lose the degree when we solve, which is fine. This is 4x plus 6x is 10x equal to 180, or x is equal to 18. So that means that our 4x angle would be how many degrees? 72 degrees. And our 6x angle would be, if you don't know how to multiply that in your head, because I didn't either, I just did 180 minus 72 in my head, and I got 108. Because they're supplementary, so they have to add up to 180. Sound good? Still familiar, right, from geometry? It's just been a minute. Some of us 2-3 years, right? Now here's one thing that may not be all that familiar for you. Yes, we can measure degrees, but degrees can be broken down into even more smaller or intricate pieces called degrees, minutes, and seconds. This is really helpful when you do navigation degrees. So when you're talking about longitude and latitude, that's going to be the most realistic place you're using this, but we can break a degree even further down into its minutes and seconds. So when we're talking about minutes and seconds, we're adding symbols beyond the degree symbol to get really specific about that degree. So we're not using decimals here, we're going to be using minutes and seconds. 1 minute, written like this, with a little tick mark for minute, looks like feet, but it's minutes, is 1/60th of a degree. 1 second, written like this, one with 2 tick marks, looks like inches, but it's seconds, is 1/60th of a minute, or 1/3600th of a degree. So we can use these conversion numbers, these right here, for minutes and seconds, to convert from decimal form of a degree to degrees, minutes, seconds, and vice versa. Degrees, minutes, seconds are really nice because the minutes, the seconds, the minutes, and the degrees will add or subtract together like normal straight up numbers. So if we're just adding or subtracting DMS numbers, degrees, minutes, seconds, we just treat it like an 8-year-old, yeah, you could subtract things at 8, an 8-year-old math problem. So if we're doing part A, we would do 51 degrees, 29 minutes, plus 32 degrees, 46 minutes. And you just add like you did in elementary school. So starting at the back, 9 plus 6 is 15, carry the 1. 1 plus 2 plus 4 is 7, so that's 75 minutes. We add the degrees. 1 plus 2 is 3. 5 plus 3 is 8. 83 degrees, 75 minutes. But here's the thing, if you were to type this into a computer, it would tell you your answer is not in simplified form. A minute is 1/60th of a degree. If this number is above 60, we need to add that as a degree. So how many degrees above 60 is 75? I mean, how many minutes above 60 is 75? 15. So that means it would actually be 84 degrees, 15 minutes. So your minutes number should always be less than 60. Otherwise, you can add a degree. It's kind of like the idea of carrying the 1. Or when you count on a clock, you go to 75 minutes, that's an hour 15, so you add the degree. Now in part B, we want to subtract. If we set this up like normal, and don't write this down for a second because I'm going to make you erase it anyways. If we wrote this down like normal, this would be 90 degrees minus 70 degrees, 12 minutes. If I go to do this, are there any numbers here to subtract with 12? No. So just like you did in elementary school when you were solving, like subtracting numbers, we're going to have to borrow some numbers from this. So if I change 90 degrees, and you can write this part down. If I change 90 degrees and I make it 89 degrees, how many minutes did I just borrow? 60. So really, 90 degrees is exactly like 89 degrees, 60 minutes. Once I've borrowed that number from the 90 degrees, now I can do my subtraction. 60 minus 12 is 48. 89 minus 73 is 16. So this is 16 degrees, 48 minutes. If you want to write a note for yourself of what happened here, you would say 90 degrees is same as 89 degrees, 60 minutes. Okay, so far? Now we're going to convert between different angle measures. So when we're doing the converting, we're going to use those formulas from the little clouds at the top of the paper in the main idea bucket. It says to convert 74 degrees, 9 minutes, 14 seconds to decimal degrees to the nearest thousandth, which means we are going to take each one of those numbers and multiply it by a scalar of some type, put it in our calculator, and call it a day. That means we're going to take the degrees times nothing because we want it in degrees. We're going to take the minutes, which is 9 minutes, and we're going to multiply it by its scalar to make it a degree, which was 1/60th of a degree. And then we're going to add the seconds and multiply by its scalar to a degree. Its scalar to a degree is not 60, is 3600. So we're going to do 74 plus 9 times 1/60th plus 14 times 1/36. Once you type all that in, press go. We should get 74.154 degrees. Is that what y'all got? Yep. Fabulous. Now, if we want to go the other way and we want to convert from decimal degrees to DMS, we have to work backwards, and this one takes a few steps. It's not just like throw it in a calculator and call it done. We know that 34.817 degrees is definitely going to have 34 degrees to start, but our problem is we need to figure out what that 0.817 degrees is in minutes and seconds. So we take the 0.817 and we're going to multiply it by 60, which is the opposite. Since we did 1/60 to get to decimal degrees, we do times 60 to get out of decimal degrees. In your calculator, when you do 0.817 times 60, you should get 49.02 degrees. Minutes. Fabulous. Take the whole number out of this, the 49, and count that as your minutes. We then need to take the seconds, the decimals, and figure out what that is in seconds. So like, I'm just going to put this bar to show this is something else to my brain. I'm going to take the 0.02 and multiply it, this time only by 60, not by 3,600. The reason it's only multiplied by 60 is we're going from minutes to seconds instead of degrees to seconds. So this is already in minutes. To go from minutes to seconds, it's just 60 again. If we had degrees to seconds, it would be by the 3,600. So if we multiply that by 60, you actually end up getting a decimal for your seconds, which is kind of weird, but totally acceptable. So this number, 34.817 degrees, can be written as 34 degrees, 49 minutes, and 1.2 seconds.
Why do they call them minutes?
I think it's leftover language from like naval navigation, like on boats and stuff. Actually, I've never asked that question, but I know longitude and latitude use minutes and seconds, so I have to assume that it's just, that's the language they used. And because it has to do with 60, so it's like a clock, 60 minutes, 60 seconds. I could also see it tying into that. I actually don't know. Thanks for asking. I'll probably go Google that later. Okay, getting back into looking more at angles on a coordinate grid. Again, I know I'm going really fast, but a lot of this is reminders / kind of makes sense. If we look at these vocabulary sections here, we need to know about what's called standard position. That's going to be really important for us. An angle is in standard position if its vertex is at the origin. So for both of these angles, the vertex is at the origin. And if the initial side is extending along the positive x-axis. So we see for both of these that they start at the origin and they extend to the x-axis. If you were going to draw an angle on a coordinate grid, you would probably start to draw it like this. This is very intuitive for us that this is what the starting side is going to be. We're not going to deal with angles that are not in standard position, at least for a while. They will always be centered at the origin. They will probably always, I'm 90% sure, be extended towards the x-axis. So we can guarantee like we're going to be using standard position pretty much the whole time. Which also means that your angles can extend beyond quadrant 1. We can have bigger than acute angles. We can have bigger than obtuse angles. We can have angles that go all the way around your coordinate grid, which means that if you have an angle that is, let's say, 250 degrees, 250 degrees is in this range right here, so your angle will extend into quadrant 3. If you have an angle that's 300 degrees, that's in this section, so it would be in quadrant 4. So identifying what quadrant your angle's in, just based on the degree measurement, will be helpful, especially as we get further into trig. You'll see this word again, and it's a word not that I struggle to spell, but I struggle to say. Quadrantal angles. Quadrantal angles are the angles that lie on your x and y axis. So your 90 degrees, 180 degrees, 270 degrees, 360 degrees. Those are quadrantal angles. Also 0 degrees. Now, last vocabulary word for this page is coterminal angles. Since the terminal side of an angle is where it stops, coterminal, together stopping, is kind of what that means. It means it's two angles that have different degree measurements but stop at the same place. Coterminal. So if we look at these two images here, this is a 60-degree angle. This is a 420-degree angle. Goes all the way around and up 60 more. These are coterminal because they end at the same place. If we were to draw both, the terminal angles would be on top of each other because we just move 60 or we move 360 plus 60 to get to 420. If we look at this one, same thing. This angle is 110 degrees. This red angle is 830 degrees. So we've gone all the way around, and then 110 more. Those are coterminal angles because they end at the same place. So you can have a wild amount of coterminal angles because all it is some multiple of 360 degrees. I would highlight that right here. That means that they are coterminal. So whatever angle you have, add or subtract 360, it's coterminal no matter what. So if that's the case, and I gave you the angle 908 degrees, I want to know what the least positive coterminal angle is with 908 degrees. So we've circled around the axis a few times. Let's start taking some of those revolutions off. So the way I would solve this one is by saying 908 degrees minus 360 degrees. What is 108 minus 360? 548. Okay, still not underneath 360 degrees, so let's take off another 360. So we'll take off an entire other revolution around this circle. What's 548 minus 360? 188. Since that is between 0 and 360, so it's within the first revolution, this is going to be the least positive measure for a coterminal angle. If we subtracted 360 again, we'd be in a negative number, which is still coterminal, but this one specifically asks for a positive coterminal angle. Yes?
Can we just go from 908 and subtract it from 720?
If you knew it was doubled, yes. So if you have a handle on your multiples of 360, yeah, you can subtract 720, which is 2 full rotations.
How do you figure out the initial side?
What do you mean?
Like, when you're looking at an angle, which side is the initial?
For us, it's mostly going to be that x-axis. So we are really not ever going to have an angle that doesn't start right here.
Okay.
Yeah. If it does, it will like fully mark what the initial side is. Like I could imagine there being a problem where it's like, this is your angle. Based on where that arrow is drawn, this is your initial, this is your terminal. We're probably not going to see that very often though. It's going to be starting at the x-axis. But that was a great question. Okay, part B and part C are both negative. So if we want the least positive coterminal angle, what should we do with negative 75 degrees? Add 360 because we want to go a revolution towards the positive numbers. So negative 75 plus 360 is 285 degrees. So that is the least possible positive coterminal angle. Bonus question, what quadrant would that be in?
Or no.
4. Bigger than 270 is 4. So if you remember quadrantal numbers, which is 90, 180, 270, it'll be easy to see which quadrant it's in. Less than 90 is 1, more than 90, less than 180 is 2, more than 180, less than 270 is 3, 270 to 360 is 4. Okay, again, we've got negative 800 degrees and we want the least positive coterminal angle. So just like this one before, we're going to add multiples of 360. If you can already tell how many to add, you can do it in one fell swoop. Otherwise, you add 360, add 360, add 360 till you get the smallest positive number. So this first time you'd get negative 440 degrees. Forgot my degree symbol. How dare I? Plus 360 again. We would get negative 80 degrees. Ooh, so close. Plus 360. You would get 280 degrees. That is the least possible positive coterminal angle. Now, all of these angles that we've gotten, this guy, and this guy, they are all coterminal with negative 800 degrees. I just specifically wanted the smallest positive one. So as long as you add or subtract 360, you have made a coterminal angle no matter what. Since we're just adding 360 every time, and Joelle kind of thought about this when she did adding 720, we can just generalize this into any angle. So if we were just wanting all of the coterminal angles with 60, we would just say n times 360 added to it, where you just change the number for n over and over again. So if we follow that formula that I've put the little bubble cloud around and fill in this table, we want the angles that are coterminal with 60. We're going to plug a number negative 2 into this formula to figure out what that negative coterminal angle is. So in your calculators, can you do 60 plus negative 2 times 360? You get negative 660 degrees. Fabulous. So that's, if I were to subtract and subtract and subtract, I'd end up at negative 660. But I can use this formula to do it a little bit faster, to do those multiples of 360 quicker. So if I do 60 plus negative 1 times times 360, this is negative 300 degrees. If I do it times 0, it would just be plain 60 degrees. If I do it times 1, it would be 420 degrees. Times 2 would be 780 degrees. All of these thetas, all of these angles are coterminal to each other, just multiplied by a different multiple of 360.
What if they wanted like coterminal with 70, or just change the 60 to 70?
Correct, yes. Yeah, because any multiple of 360 added or subtracted is coterminal to whatever angle you're given, 60, 70, 14, whatever. Now it is going to be helpful to recognize the coterminal quadrantal angles so that if you're working beyond one revolution, you still know what quadrant you're in. So these are your quadrantal angles. These are the ones that we need to recognize that are my axes, 0, 90, 180, 270, 360. But their coterminal versions, so after one revolution, are also important to recognize. So 0 and 360 degrees are coterminal because one full revolution ends me back up at the same place, which also means that 2 rotations, 720 degrees, we're back at the same place. Recognizing these numbers will help us realize how many revolutions we've done already. If we do a revolution and 90 more degrees, that's 450 degrees. If we do one full revolution and then 180 degree more, that's 540 degrees. If we do a whole revolution and 3 quadrants worth of more, 270 plus an entire revolution is 630 degrees. These are just helpful to recognize if you can, because then you, again, would know what quadrant you're working in. The main thing I need you to recognize is these 5 numbers so that you know what quadrant you're working in. Because beyond that, you can just subtract 360 and look at its coterminal side and know what quadrant you're in. So those are the super duper important ones. Our last bit for this first section is analyzing revolutions of a disk drive. It's really helping you realize what we did with the degrees, minutes, seconds conversion and converting between different units of measurement. It says a constant angular velocity disk drive spins a disk at a constant speed. Suppose a disk makes 480 revolutions per minute. Through how many degrees will a point on the edge of the disk move in 2 seconds? Here's the things we know. We were given that this makes 140 revolutions per minute. If we were to write that with units as a fraction, you would say this is 480 revolutions per 1 minute. Those of you who are in science classes will recognize conversions. When you're converting from units to units, you need the units to cancel out. So the first thing I notice is that I'm working in 2 seconds. I have this in minutes, which means I need to convert it to seconds. How do you convert from minutes to seconds? Yeah, 1 minute is how many seconds? 60. But we need the minutes to be on opposite sides of this fraction so that they cancel out. So 1 minute is 60 seconds. We will eventually divide by 60. But we're going to do all of the work first to convert. So we have to put numbers in a calculator 1 time. Now again, I put minutes on top because it will cancel out with the per minutes from the given. I also know that it's asking me to get degrees. Okay? I need to get rid of the word revolutions because it doesn't ask me for revolutions at the end. So how many degrees are in 1 revolution? Yeah, 1 revolution means all the way around is 360 degrees. These revolutions will now cancel out. The units I have left showing are degrees per second, which is what I want. I want to know the degrees in some amount of seconds. At this point, we can just take all the numbers on top and multiply them and divide them by the numbers on the bottom. So we would, in a calculator, do 480 times 360 divide by 60. Which, yes, if you didn't have a calculator, could be done a lot easier by canceling some numbers out. But we have a calculator. Let's use it. 480 times 360 divide by 60. Bleedity blop, calculator question. It's 2,880, oop, that's not the right number, 80 degrees per second. Cool, that doesn't answer the question because the question says, how many degrees will a point on the edge of the disk move in 2 seconds? So in 2 seconds, how many degrees does it move?
5,760.
Yeah, the disk rotates 5,760 degrees. How'd you get that number? Yeah, the number we got in degrees per second times 2 for 2 seconds. So when you're converting numbers, again, you always want the units to cancel out until you're only left with the units you want at the end of the problem.
Why didn't you do the revolution first?
Personal choice. You could do the revolutions first if you wanted. Because it's all multiplying and dividing. Not that multiplying and combining can go in any order, but you can multiply in any order and get the same number.